Welcome to the ASMR chemistry classroom. So glad you're here with me, and I am going to be creating a video today that is based on a request, and I'm going to venture to say that this is one of the perhaps fastest turnarounds on a request I've ever had, and it's because this person asked for a lesson on crystal field theory. And this is one of those topics that I can do with no preparation whatsoever. I know this so well, like the back of my hand, the front of my hand, I know it. So I thought, hey, I can just sit down on a lovely Sunday afternoon, spend a few moments with you, and talk about crystal field theory. Now, this topic, this is in chemistry. I once had a physicist come to my talk on crystal field theory thinking that I would be talking about field theory, which is a topic in physics, but instead, alas, they were a little surprised. I can't say they were disappointed because they did enjoy it, but it wasn't about what they thought it was going to be. Crystal field theory is an explanation, a description of bonding that occurs with coordination compounds. This is transition metal compounds. I'm showing you here one type of structure that is one of the most common, but there's also tetrahedral. I am going to be focusing on crystal field theory of octahedral complexes in this introduction video to the topic. Okay, there is a lot more to this topic, so I'll be focusing on those fundamental ideas and concepts with this theory. Okay, the things that are going to help you the most when you're first starting out and learning about it. Okay. So I want to grab the periodic table that I have over here. Okay. And I want to bring the periodic table. What is that squeaky noise? My chair. Okay. No, squeaking and turning is not always a bad thing, right? ASMR videos. All right. What I wanted to talk about here on the periodic table is that we are really focusing on the metals in this section here. These are the transition metals, and this is known as the D block. And there are some beautiful, very stable compounds that form with the 3D metals, 4D metals, and 5D metals. Okay, now this period here, these are not going to be considered because these are elements that are created in particle accelerators, so they're not going to be stable. Okay, but in theory, if they were stable elements, then they would have analogous compounds to what we see in the 3D, 4D, 5D. Okay, so these metals, they form compounds that can be octahedral, such as what I am showing you here. And there are two major theories with how this bonding occurs and how the d orbitals are involved. Okay, and the first one that is the most fundamental, that is usually taught first, is called crystal field theory. This theory works very well to explain the orbital energies of the d orbitals, and it works well to explain some of the colors that we see and other spectroscopic parameters that are observed for these types of complexes. It also helps explain magnetism, magnetic properties that we see with many of these transition metal complexes. And it is all based on the d orbitals. Okay. So this is bonding. Crystal field theory is another way to talk about bonding between transition metals and ligands. Okay, and then what's a ligand? Okay, so generally these are non-metal molecules and ions that can bond to the central transition metal. Okay, so the primary types of structural geometry that you will see usually octahedral, tetrahedral, or square planar. Okay, all these three structures are the most common. It's not to say there aren't others, because there are, but these are the three you'll see the most common, and we're going to focus on octahedral in this video. Okay. So generally, what this looks like when you have an octahedral complex is it looks like this. Okay, we've got metal, transition metal in the center, and then we have our four ligands in what's sometimes called the equatorial plane, and two ligands axial. All together, this is 6 ligands. Okay. So sometimes this is written generically as ML6, signifying there are 6 ligands. And we can also draw this out using our kind of wedge notation, these wedges coming closer to us, and then these dashed wedges going back, where there's a ligand in each of these locations. Okay, so this is the structure we're talking about. This is the general formula we're talking about. And now I want to get into crystal field theory, focusing on the d orbitals. Okay, so here is where we begin. And why don't we use a metal ion as an example so that we can focus on a particular metal with the electrons and have something to go by. So let's take a look at chromium plus 3. Okay, let's look at chromium plus 3. And if we have chromium plus 3, we want to know how many d electrons there are, because that's going to be relevant when we are talking about the d orbitals. All right, so how many d electrons? So we want to know where are those d electrons in those d orbitals. Okay, so a nice place to start is writing out the electron configuration. So if we look at chromium, electron configuration, it's the same as argon, and then now the 4s are being filled, and then the 3d. Okay, so our electron configuration of neutral chromium looks like this. 3d4. Okay. And then one might argue, oh, well, it's actually argon 4s1, 3d5. Okay. Because of some inherent stability to half-filled d orbitals. But honestly, this, whether it's this or this, becomes moot when we ionize it to make chromium plus 3. Okay, so chromium plus 3, the orbitals, the 4s orbitals, are actually higher in energy than the 3d. This has to do with the effective nuclear charge and the ability of these orbitals to penetrate close to the nucleus, and how d orbitals are poor at shielding, all sorts of aspects like that. But the main point here, for all transition metals, electrons are lost from the s orbitals first, before the d. So that means we are losing 3 electrons where we first take them from the s orbitals, okay, whether we write it like this or like this, and the remaining come from the d orbitals. So ultimately, this chromium plus 3 has an electron configuration of argon 3d3. There are 3 electrons. Okay. So if we had the free ion floating around in space, say perhaps for some reason we have chromium plus 3 is floating around by itself in outer space, or in a reaction chamber in a laboratory, or whatever the case may be. If we have this free ion, nothing surrounding it, it would have 3d orbitals that are all degenerate. Degenerate means the same energy. Okay, there's no reason to believe that it would be anything other than this. And then we would put in those electrons. Okay, let me grab another color here. There are 3 of those d electrons. Put those in. 1, 2, 3. Okay. Now, here is part of crystal field theory. The premise of crystal field theory is that you have these ligands that come in and they interact with the d orbitals. Okay, what are all the d orbitals? Let's acknowledge what they all are. There is a dxy, there's the dyz, dxz, dz squared, and the dx squared minus y squared. Okay. Now, these d orbitals, their shapes, where the lobes are, is very relevant to how they interact with the ligands, all right, and where those electrons then are. Okay, so sometimes, depending on what course you're taken, or you have taken, or you are taking, you don't necessarily need to memorize these shapes. But if you're learning about crystal field theory, it is very helpful. Okay. These two, the dz squared, dx squared minus y squared, these are orbitals that the lobes lie along the x, y, and z axes. Okay. I actually made a video where I draw out all the orbitals, but just real quick, draw these these out, the dz squared looks something like this. Okay, this is the z-axis. So we have these lobes that are along the z-axis. Okay. Meanwhile, if you have, I'll keep the z here, and then if we have x-axis, and then I'll try to make it smaller, thinner, going back, and then this is the y-axis coming out at us, a little bit thicker because it's coming toward us. And then here I'll draw it going away, back, away behind the paper. Okay. If these are the axes, the dx squared minus y squared, here I'll label this dz squared. Okay. The dx squared minus y squared orbital looks like this. We have a lobe along the x-axis and along the y-axis. Okay, I'm drawing the ones that go back last so I can show how they kind of go behind the ones that are in the front. Okay, so see how these lobes are along the axes. These axes, this is where those ligands are coming in. Okay, so I drew the structure up here. This is like the z-axis. Here's the x-axis. Here's the y-axis. Okay, so that's saying the ligands are coming in, interacting down below along the z-axis, from up above z-axis, from back behind x-axis. See, all 6 ligands are interacting with these d orbitals, these 2 specific ones. Okay, so the premise of crystal field theory is that when the ligands are along the axes where there are lobes of orbitals, those orbitals will be perturbed more, higher, raised in energy. Okay, so the ligands coming in will raise the energy of the dz squared and the dx squared minus y squared. Okay, now I'm going to draw these dashed lines to show that there is now a splitting that occurs of all of these d orbitals. Okay, so of these, I want to make sure I get these going down, but not quite as steep of a slope there. Okay, so as I said, the dz squared and the dx squared minus y squared orbitals, because of those ligands, these are raised in energy. Okay, and then you can think about conservation of energy. If these go up, these other ones go down. So that means the d x y dy z and dxz lowered in energy. This splitting is key to transition metal chemistry, transition metal complexes, and it is known as delta. And in the case of an octahedral compound, also known as, now it says this is in an octahedral field, those ligands coming in, so we put an O there. O is for octahedral. If it were tetrahedral, we'd put a capital T there. Okay. So what about those electrons? Okay. Those electrons will go into these lower lying orbitals. 1, 2, One other thing that is observed, notice how these three orbitals do not go down equally to the amount of increase of energy of these two. Okay, these go down by a little less because there are three of them. So in terms of weighting, like WEIGHT, this is weighted further with these three, so they don't need to go down as much because there's three of them, whereas these two go up a little bit more. But the split is designated as delta O. So in terms of that weighting of splitting, you take that into account for certain types of problems, but if you're going into the lab and you're measuring with a UV vis spectrophotometer, you would be measuring this absolute difference in energies. Okay. So notice here how we have three unpaired electrons when we are in this octahedral compound, metal with 6 ligands. Okay. But we get some very interesting possibilities when we have transition metals that have more than 3 electrons. Okay, so let's take a look at an example of that. How about if we just looked at chromium plus 3, we could actually look at chromium plus 2. So what about chromium plus 2? Okay. So if we had, why don't we draw a little separation here? Chromium plus 2. Okay, take a look at this. Alright, so let's do the same kind of thing where if we had chromium plus 2, we're still looking at octahedral, so we would still expect there to be a splitting in energy that had some magnitude associated with it. Okay, but now how many d electrons do we have? Okay, so now we are removing 2 electrons, and chromium plus 2, this has 4 d electrons. Sometimes we refer to chromium plus 2 as a D4 metal. If it had 6, we would say D6. So that's just a terminology that sometimes comes up with transition metal chemistry. Okay, so we look at what we have here, and we now have a conundrum of sorts. And that is, we have 4 electrons, so put in the 3. That 4th electron, it could either pair up with one of these. Okay, we'd probably conventionally put it there. Okay, that'd be following Aufbau principle. But when you pair electrons, there are some pretty strong electron-electron repulsions that can happen. Those are called Pauli forces, after Wolfgang Pauli. Okay. Anyway, we have electron-electron repulsions. So in some instances, it's actually more feasible energetically to keep them all separated and follow Hund's rule. And this electron goes up into a higher energy d orbital. There are other cases where So I'm going to put an or here because both of these are observed. It's octahedral, so we still have the same splitting pattern with 3 down below and 2 up above, where in this compound we've got these 3 electrons and the 4 that does pair up and go into the lower level. Okay, so this begs the question, how do you know which one it does? Okay, now you can go into the laboratory and you can measure what's known as magnetic susceptibility, which is an indication of magnetism, how many unpaired electrons there are. This chromium plus 2 in this compound that it's in would have 4 unpaired electrons, whereas this one would have 2. So going into the lab, you could measure and figure it out. But what if you could not go into the lab? What if you wanted to predict which one it would do? Okay, this is where we can look at ligands and determine what's going on here, which one would it do, and try to make a prediction. But I'm going to point something out here to you, okay? Both these cases, we have a delta, right? We have a splitting. Notice how, and I did not do this randomly, I did this on purpose. This one is larger. And in the case where delta is larger, these electrons paired up. In this case, where delta was smaller, the electron ended up in this higher energy orbital. Okay, so this is a phenomenon where when we have a small delta value, it is more energetically feasible for that electron to go into that higher energy orbital. And unlike over here, it was not destabilized by having paired electrons. Okay, this is called high spin. High spin. So spin is referring to the spin of the electrons, where this electron, that spin, went up into the higher energy orbital. Okay. This occurs when there is what is known as a weak field ligand. Such as halides and oxygen-based ligands. This occurs for 3D metals. If you have a 4D metal or a 5D metal, they will always be what is called low spin. Okay, so this question of whether it will be high spin or low spin, where it depends on the ligands, this is only a question for 3D metals. Okay, so in this case, we have a large delta. Call this low spin, as I just said. Low spin, because that spin now is down in the lower energy d orbitals. And this happens with what we call strong field ligands. Examples of strong field ligands are nitrogen-based ligands. Phosphines. Those are molecules that have the form PR3. It also includes molecules such as CO, CN, there are more, and other what are called pi acceptor ligands. Okay. All right. So this delta you can predict by looking at what are the ligands that are around that central metal. And you can determine whether or not to be high spin or low spin. I do want to just reiterate that for 4D and 5D metals, they are always, and I'm going to say for octahedral, I wrote of, meant for, I think octahedral, and then I wrote an O. For octahedral, low spin. Okay. So even if you have a halide ligand like a chloro ligand, or if you have an aqua ligand, a chloro would be a chloride, aqua would be the water molecule as a ligand, you would still, if you have a 4D or 5D metal, it would be low spin. Okay. And that is because these 4D, 5D orbitals are so large that they interact greatly with those ligands and they cause a large splitting for the delta. Okay. All right, so everything we've gone over is all this basis foundational knowledge where we are looking at the d orbitals, we're looking at the splitting pattern. Here we focused on octahedral, and we see that the delta that's split can be small or large. That will impact whether our 3D metals are low spin, well, I should point at the correct one, low spin or high spin. Okay, and then we also keep in mind when we have 4D, 5D metals, they will, for octahedral complexes, they will always be low spin. This is the springboard to other topics in crystal field theory. We can look at what's called Jahn-Teller distortion, which causes a little bit more loss of degeneracy, these orbitals. We can look at what the UV visible spectra would look like. Okay, we can look at colors versus looking at what that splitting is. We could also look at tetrahedral compounds, what those look like, same with square planar. All right. I spend many, many weeks on crystal field theory and talking about transition metal compounds. So this is a huge topic, but it does begin with looking at these aspects of the d orbitals. And I would say it does help a lot to recognize that there's an origin that has to do with the shapes of these orbitals and how they are overlapping with the ligand orbitals. I want to end this talking about crystal field theory with stating that crystal field theory is a very good theory in terms of being able to identify things like whether it's high spin or low spin, and in a hand wavy kind of way what the splitting looks like. But there is a more sophisticated model, more sophisticated theory called ligand field theory that looks at everything from a molecular orbital theory point of view. It is actually more accurate, and it's, like I said, it gets a little bit more complicated. That's why it's not taught first. Usually we teach crystal field theory first. But like I said, this works pretty well for many things that we are interested in, such as magnetism and spectroscopy. So that's why we start. all of you who needed a primer on crystal field theory, I hope this was helpful for you. Or if you really don't care much about crystal field theory at all, but you just wanted to hear me drone on and on about chemistry of some sort, this probably worked for that as well. So, okay. Let me know if you'd like me to continue on with other topics related to crystal field theory. Very happy to do that. And other topics as well. I am going to be creating more and more videos. My goal is to have an entire general chemistry curriculum, essentially, lessons on pretty much any topic that you might see in general chemistry. And I would also like to create a series of videos that are introductory organic chemistry videos and a few special topic ones as well. So let me know what will be helpful for you, and I will get on it. Okay. Thank you as always for your likes, for the subscribes. That helps me a lot. Also, thank you so much for sharing these videos with people whom you know that these kinds of topics and these lessons will help, whether it's help learn chemistry better or help sleeping. I really, really appreciate it. I have been doing this almost 5 years. I'm trying to figure out what I should do to celebrate 5 years. So I will think about that. Let me know if you have any ideas. And in the meantime, I'll just keep rolling with it and keep teaching all of you and keep showing up for you. Thank you so much. I will see you in the next video.